Good afternoon. My name is Alec Leckey. I'm a researcher in the Intel Labs organization of Intel. The focus of our lab is software-defined infrastructure, SDI. I know some people prefer the acronym SDX, but we're talking about the same thing. And my own focus is on the networking pillar of that. I'm also the project lead for the NetIDE project of OpenDaylight. We're a relatively new project within the consortium. And we're since the Beryllium release. And our focus has been on looking at interoperability between different SDN controllers. And indeed, if you had a legacy application, how could you easily migrate to OpenDaylight with as much ease as possible without having to go and rewrite that application? So when you talk about SDN controllers, the thing is, there is quite a lot of them. Hang on. Sorry, bear with me. Oh, sorry guys, PowerPoint is after crashing on me, so give me 1 second. Okay, back again. Yeah, so I was talking about SDN controllers. So there is quite a lot of them out there. You know, and some of the earlier versions would have been probably little more than open flow abstraction layers. But over time, you know, these have matured, and you'll see, you know, multiple southbound protocols. That's not even a full list. But they all have different execution models. They all have different programming models, APIs, and different features. And they've kind of progressed into nearly SDKs for SDN. And I think OpenDaylight's the perfect example of that. You know, they're easily extendable. I think we had 40+ projects in the Beryllium release. We'll be easily 50+ going with Boron in September. And indeed, you can see the APIs will be different as well, whether you go REST or whether you go native. There's even the JavaScript one, which kind of led me to fear that at some stage over the weekend, somebody will code a one in COBOL. But I think the point is that we'll probably see more SDN controllers appear in the future. And these are only just the open source ones. I could have done a completely different slide on some of the proprietary ones that exist out there as well, and we'd be having the same issues with regards to API. So again, if you have an application and you're developing it for an API, you're essentially going to be landlocked to that particular controller. How can you easily migrate? So, and that's what we're looking at. The fact that the feature list of the controllers are slightly different. So one solution does not fit all, depending on what your requirements of your application is. How do you develop an application to reconfigure your network accordingly? What kind of UI, what IDE are you using? And then when you deploy your application, how do you debug it, troubleshoot it, and ensure it's working as you expect it? So this is the standard hype curve that people would be familiar with. It's the networking one. It's from last year. You can see that software-defined networks is down at the bottom of the trough, which I think probably makes sense. You know, SDN controllers are starting to mature. They're becoming a little bit more robust. They're becoming genuinely data center grade. You know, high availability clustering, many tens of thousands of switches supported, especially by OpenDaylight. And then SDN applications are up here at the top. So our anticipation is we're going to see quite an explosion of SDN applications appear over the next 12 to 18 months. And so we're kind of looking at preparation for that as part of the research. So again, I'm flagging that if you do go and pick a particular controller, it's not easy to port to a different controller without having to rewrite. It's not easy to combine. So if you build up a repertoire or a collection of applications that run on your network. How can you combine them into a super application based of them? And lastly, if you do want to deploy them, how can you debug them easily? And although there are a number of tools, they are specific to a controller in question. So wouldn't it be cool if you could debug an SDN application irrelevant of the controller that it was running on? And this is where NetIDE comes in. Now, that's quite a lot of research areas to try and potentially look at. But what we are looking at doing is creating a very simple, integrated SDN environment that will cover the whole life cycle of an SDN application, from the design, the development, deployment, debugging, and running it on your network. We're trying to do it under the rules of platform independence, that you can reuse apps, reuse code, and you can run your developer tools irrelevant of the controller you've selected. So this is the project architecture within our project. So we start up here with our developer who's sitting at a single IDE and is either coding an SDN application from scratch, or they're potentially pulling out of an application repository an existing application that they may have purchased or developed previously, and they're looking to literally assemble applications together to form a super app. So each one of these standalone would be its own SDN application, but when you combine them together, we use the term modules, but it's just a standalone SDN app. And is it possible to take existing standalone SDN applications, combine them together as modules, and kind of assemble then a super SDN application? So the question becomes, if you don't count which controller the application was written for, how are you going to deploy it? And we deploy it using the NetIDE network engine, which is part of the OpenDaylight Beryllium release. And the way it works is we've kind of split it up into concepts we've borrowed from ONF's SDN architecture document, which is client controllers and server controllers. So server controller basically manages your physical and virtual network. So it's connected to the switches. It's sending down the flows. It's receiving the events. But through a northbound plugin, which we call the shim, and this is what the NetIDE project is within OpenDaylight, we're exposing an API to allow other controllers, which we call the client controllers, to be able to communicate with the network infrastructure. And they do that through a suite of backends. So the backends are custom to a controller in question. So whether it's a Ryu or it's a Floodlight or whatever, that backend is specific. And it means that that controller can send out communique, send out network protocols, and the backend will pick it up and then will route them through their shim and in the server controller out to the network switches. Now, our first design, the backends talked directly to the shim. And our prototype worked and it made sense. But we found that the backends were actually quite rich. There was quite a lot of functionality in them. And if you come along and say, we've been evaluating this particular controller, how do I use your system? And I just go, it's simple. All you need to do is implement the intermediate protocol in a backend. And because the backend was so rich, it was quite a lot of programming. So what we did was we pulled a lot of those features out of the backend and the shim and put it in this middle layer, which we call the core. And it means the backends are extremely light. All they do is they intercept the traffic. There's a couple of other items they do, and I'll go through later on. And they route the traffic then through the core. So you're talking about maybe 5 or 6 interfaces you just need to implement if one of the controllers you use, and if you want to implement a backend for it. So if I talk about an implementation of that, here's one here. So we see OpenDaylight with its high availability, with its clustering, and its data center running as the server controller. It's managing all the different network elements, be they physical or virtual. We have our NetIDE project, which is the same, shim. So you would just do from the Carafe command line, if people are familiar with OpenDaylight, you just do feature install NetIDE. And then you'll be running the core, which kind of collects all the information coming from the backends. So we have backends for Floodlight, which means that when you deploy an SDN application, it's getting the API it expects. So if it's written for Floodlight, it'll run on Floodlight. And then the backend will redirect those messages. So Floodlight, no different to OpenDaylight, has a web interface, So you can go into the topology map and you can see what the map of your switch is, what your topologies is. Even though Floodlight is not directly connected to any switches, but you'll see the exact same diagram you would that if you ran the Deluxe web interface on OpenDaylight, in which you'll see the exact same switches. So Floodlight thinks it's managing the switches, but the back end will route the traffic through the core. And it's the same for Ryu. And if you came along and said, you know what, we've been evaluating a different ONUS, for example, as a controller. We have a few applications we'd love to run on ONUS, but our network infrastructure is managed by OpenDaylight. All you would need to do is just implement a back end. And you could leverage maybe some of the Floodlight, because they're both Java related, and just implement the NetIDE intermediate protocol. One of the cool things is, because all traffic is being routed through the core, it means we have visibility to all the messages that are going north or potentially going south. And we can look at things like combining applications together. Because the core doesn't care where it's come from. It's seen the messages coming in. It can combine them together. And whether that application runs on Floodlight or whether that application runs on Ryu, we can combine them together. Because at the end of the day, it's just a message going towards the switches. Which means, in addition to application composition, we can take a look at potentially solving or providing an initial solution to the multiple write problem, which is that when an application subscribes to switch events and it sends potentially a packet out to go and put a flow on a switch, multiple applications may actually be subscribed to that event, and as a result send multiple packet outs with conflicting actions for that particular packet. And there is no solution at the moment other than whoever arrives second will overwrite the first. So the fact that all the traffic is routed through the core, we can potentially spot the same actions coming for the same event and implement some sort of policy on how we want to do conflict resolution. So to implement a backend, all you need to do is implement the NetIDE protocol. And before you go, oh, I have to read a document, I have to go through it, and how am I going to implement it? We have a Python library that implements it with a number of methods, and we have a Java library that it does exactly the same. So I'm really just kind of giving you the high-level information to know exactly what's going on behind the scenes. But all you would need to do is just import whichever library you were needed, depending on the back end you were going to do. But you can see some of the basics about it. We've got our own version numbers. I think we're at 1.3. And we have some new requirements that we'll do. So I think we'll be 1.4 when Boron comes out. The type, which is kind of leverages the same methodology as the way OpenFlow works, but the type describes what's contained in the body of the message. So it might be an OpenFlow packet that's going north or south. It may be a netconf. It actually may be some of the NetIDE specific information. So it might be the announcement of a new backend, new client controller that's appeared. And on that client controller, there might be a new SDN application running, which we call a module. So you'll see things like a module announcement and a module acknowledgement. The core is aware of it, and it has assigned it a new module ID. And the module ID you'll see here. And this is important because as client controllers send requests down to the switches, so maybe, for example, a stats request or a get config, and there are multiple client controllers, and each one of those has multiple applications running on them. We can track that message as it goes south. So when the reply comes back into the core knows which client controller originated that request, and we can send it back and respond to it. And of course, the data path ID, which switch in particular the message was assigned to. So in our documentation, we have all the swim lanes, and I've just kind of described that, where a module, an SDN application, sends the request out, the backend picks it up, it assigns it transaction ID and a module ID, and it sends it all the way down to the switch, and then how it bubbles back up again. But again, as I said, our two libraries, the Python library and the Java library, will do all that for you. So all the traffic is going through the core, and the core basically implements three kind of features. It's the interface between the different backends you might have running and the actual shim, which is talking to the switches, and managing connections. It manages the messages going north and south. It orchestrates the execution of the different modules. So if you're going to combine them together, and coordinate the messages as they go south and then potentially as they go north as well. So we need to track those messages and send them back to the correct controller. We also have our composition layer as well. So as we take each of those together and combine multiple SDN applications as modules and create a much richer application, composition will look after that through assigning it module IDs and tracking the messages. And then we've got our conflict resolution as well, and I'm going to go through them next. So the thing about application composition is it allows you to combine existing standalone applications together. So if you take four simple SDN applications, like say a NAT service, a layer 3 forwarding, and a layer 2 forwarding, and a monitor application. The things you need to set up in advance would be the semantics of how you're going to compose. And we've borrowed these from the likes of FlowVisor, which have been looking at it, or FlowBricks, or even the Pyretic language as well, which runs on top of the POX controller. And they are, do you want to run them sequentially, which is the plus symbol? Do you want to run them parallel, which is the double greater than sign? Do you want to group them together, so which is just the brackets? And eventually, as they both spit actions out, which need to go down to the switch, you're going to potentially have to merge different packets. And we use the curly bracket for that. So a typical scenario might be an event is raised by a switch, and it's going to be sent to this application. So you're going to see potentially a packet in going into the NAT first. And the NAT's going to process it, and it's going to spit a packet out, which would normally go straight to the switch. But because we're doing composition, and we're doing it in parallel, we're doing it in sequential order, the layer 3 forwarding module is going to get it next. Now, a layer 3 forwarding can't do anything with a packet out. So what we need to do is we need to take the actions that were put in the packet out and put them back in to the packet in that went in here originally. So this is going to get a packet in with new modified actions based on how that NAT worked. And similarly, the layer 3 forwarding is going to operate on that packet. It's going to generate a packet out. Again, we need to modify the packet in with the actions for that. And because we've got the layer 2 forwarding and the monitor running in parallel, both of them will get that packet in simultaneously. And they will process them. They will both spit packet outs potentially. And now we need to merge the actions that are coming from the layer 2 forwarding and the monitor together before we can send that down to the switch. So how difficult it is to code an application, multiple applications together and combine them and do merging and so forth. And the answer is, it's just a simple XML file. And all we do is we list the modules that make up our application, assign them unique IDs, and that allows us to track messages that are going through the core, down to the switch, and back up again. So it's just a matter of listing them. The next thing you need to do is you need to specify how you want the execution to flow, and that's the execution policy. So you can see I've done it here. We've got a module ID, which is the NAT, which will get the packet first, the L3 forwarding. We've got some default actions, so if you don't get a packet out, for example, we might call that just a drop, so that's the result action. And then we've got our parallel call, and we've set up that the module, the level 2 forwarding, and the monitor are going to run in parallel. And here is where we can specify the resolution policy for conflicts. Although we have a number of choices, we can say ignore, which is what currently happens. You can do discard, where you may discard a later one. We're going to use priority in this scenario, which means if you get competing actions on the same header, then what you'll do is we're going to prioritize. We're going to say the monitor application takes priority and the level 2 forwarding does not. We'll lose out. And that's just one potential way we can run resolution. And that's how we combine it. So it's an XML file that just combines those four modules together. And we don't worry about which client controller that they're running on, and we can manage that. Our problem, though, with regards to conflict resolution, is inherent in OpenFlow, and that is, how do you know when a module is finished processing an event? And this is called the run to completion problem. You don't know, and that is, if a module receives a packet in, you don't have to respond with a packet out. Therefore, if you're sitting there and you're waiting, you've sent the packet in and you're waiting, how do you know the application is not going to respond, because it doesn't have to, under the protocol specifications? How do you know it's just processing and it's taking a long time? So do you take all your responses? So let's say there's 4 applications there. They run in parallel. They all get the packet in. And we're starting to get packet outs. We know the module IDs. We know they all relate to this application. We get 2 back. Do we start merging now? Do we wait for more to come in? Do we send that packet down, all of a sudden another one comes? We don't know, and this is our problem. So what we've been proposing is that we would come up with an end of processing marker, which we call the fence message. And that is basically that as a packet comes in, and then a module generates a packet out, it may even generate a flow mod later on, and more packets come in, that we can track based on the module ID and a NetIDE transaction ID, which is the NX ID, that we can know that as soon as we receive the fence message from the controller, that we can go and say, right, we're finished. The merge of the packet outs can now occur based on our conflict resolution policy. The problem is not all controllers support this message. In our prototyping, we've been using Floodlight and Ryu. And with Ryu, because Ryu is Python, the way our backend works, we can actually intercept and know when Ryu is finishing processing a message so we can send it down. But Floodlight out of the box does not support that. Now, that's not to say you can't use NetIDE to run a Floodlight application. We're just struggling to get Floodlight to run with application composition in this scenario. So what we have done is we have proposed a change to Floodlight, which is a simple little interface, which is the control complete listener. And we have submitted that patch to Floodlight, which they've accepted on their master branch. And it means that within Floodlight now, when a module of Floodlight is finishing processing an application, it will send, I think it's a done method, just say we're finished. And it means that the fence message is there, and then composition, conflict resolution can occur based on that. I was originally going to do a demo, but it's only when I went through my slide deck I realized I was never going to have time to run it. But this was the scenario. We would have OpenDaylight running, and we'd run Mininet, and we'd have a number of switches running. We'd have a number of kind of clients running as well. And we would use Floodlight as a client controller. We would use Ryu as a client controller, and we would run 2 applications, a learning switch and a firewall, and we combine them to form a composed application. So they're both managing the same network, but Ryu is setting up this switch to be a firewall. So the demo would have been kind of like both Alice can ping the web server, Charlie can ping the web server, and I would have been able to show that in the console. But Alice can't ping Charlie because Charlie's behind a firewall. So what you have is you have 2 applications that are both combined and cooperating on the same network, even though they're actually not aware of each other. Now, if people are interested in this demo, I can potentially spin up the VM that contains the demo, and I can show you offline. I'll be walking around for the rest of the day. But you would have seen the traffic through the different consoles running up that way. The thing about NetIDE is it's more than just what we've been working on within OpenDaylight. I talked earlier about the IDE and developing, deploying, and testing. So you can also download an IDE that allows you to design using dragging and dropping of switches, of setting up ports, and configuring your network irrelevant of the API of the controller you're working with. You're literally just right-clicking and you're setting it to be a firewall, you're installing rules. And then we have auto code generators that will then automatically go and generate the relevant code based on the controller that you've selected. We don't obviously have all controllers covered at the moment, but we have done a few of them as well. And of course, the cool thing is you'd have the relevant, all within one IDE, you'd have the relevant consoles available there to allow you to go and play around and see it's working. Again here, it's just another screen capture of the IDE. You can see you're just dragging and dropping. In this scenario, we've got a headquarters. We have a remote branch. with a number of switches, and then you've just dragged and dropped the relevant components in to form that network topology. And then if you right-click at the end, it'll allow you to deploy it. So we've been using Vagrant and spinning up VMs, and depending on what client controller you were running, you'd be able to spin up that VM, we'd be able to start that module, and then the core would pick it up and allow it to run on top of OpenDaylight. Additionally, we've been looking at some developer tools. So because the cool thing about the core is it has visibility to all messages that are going southbound towards the switches from the different clients, and similarly all events that are going north. So it's very easy to kind of log all those and then make them available to a number of debugging type tools. So kind of ones in particular might be of interest, might be a model checker. So as you design and drag and drop your switches and you want to reconfigure your network accordingly, is that actually deployable on the physical network infrastructure that you have in your organization? And so it allows you to confirm you've set that up. The profiler is kind of interesting. So you can potentially kill a particular switch. What will happen to your traffic flows based on that? And it'll kind of profile failures within your application. And then the debugger is kind of based on the likes of OpenFlow Replay, where you can see packets and flow checking. So if you want to find any follow-up information on the project, on how we're doing it, your starting point would be the OpenDaylight wiki. This is the NetIDE project up there. If you're interested in how we've done the IDE, we've put up an initial version on the Eclipse Marketplace. You can feel free to go and download and play around with it. If you like the IDE, or if you want to get the code for any of the backends, or any of the tools that I've kind of very high level gone over, if you go to our Git presence, if you do a search on FP7 NetIDE, you'll find the code for them there. The code for the shim component, because it's part of OpenDaylight, doesn't reside under our project repository. It actually resides under the OpenDaylight Git repository, so you'll find the code for that there. And then we'd have the standard social networking stuff, like we have our Twitter feed for announcements and what the project's currently working on. But also, which is more interesting because I didn't get time to do it, we do have some videos of demos up on YouTube. So if you want to see that network engine running two different applications, with Floodlight, with Ryu, but on top of OpenDaylight managed infrastructure, they're only about like 6 minutes long. So you can go up on YouTube and you can see some of the demos running there. So with 3 minutes to spare, thanks for your time. And if anyone has kind of any questions on how we're running the project, or just let me know.
Are there any questions? All right. Well, thank you very much, Alan.
OK, thank you very much. So we see more SDN controllers appear in the future. And these are only just the open source ones. I could have done a completely different slide on some of the proprietary ones that exist out there as well. And we'd be having the same issues with regards to API. So again, if you have an application and you're developing it for an API, you're essentially going to be landlocked to that particular controller. How can you easily migrate? So, and that's what we're looking at. The fact that the feature list of the controllers are slightly different. So one solution does not fit all, depending on what your requirements of your application is. How do you design, develop an application to reconfigure your network accordingly? What kind of UI, what IDE are you using? And then when you deploy your application, how do you debug it, troubleshoot it, and ensure it's working as you expect it? So this is the standard hype curve that people would be familiar with. It's the networking one. It's from last year. You can see. So good afternoon. My name is Alec Leckey. I'm a researcher in the Intel Labs organization of Intel. The focus of our lab is software-defined infrastructure, SDI. I know some people prefer the acronym SDX, but we're talking about the same thing. And my own focus is on the networking pillar of that. I'm also the project lead for the NetIDE project of OpenDaylight. We're a relatively new project within the consortium. And since the Beryllium release. And our focus has been on looking at interoperability between different SDN controllers. And indeed, if you had a legacy application, how could you easily migrate to OpenDaylight with as much ease as possible without having to go and rewrite that application? So when you talk about SDN controllers, the thing is, there is quite a lot of them. Hang on. Sorry, bear with me. Sorry guys, PowerPoint is after crashing on me, so give me 1 second. Okay, back again. Yeah, so I was talking about SDN controllers. So there is quite a lot of them out there. You know, and some of the earlier versions would have been probably little more than OpenFlow abstraction layers. But over time, you know, these have matured, and you'll see, you know, multiple southbound protocols. That's not even a full list. But they all have different execution models. They all have different programming models, APIs, and different features. And they've kind of progressed into nearly SDKs for SDN. And I think OpenDaylight's the perfect example of that. You know, they're easily extendable. I think we had 40+ projects in the Beryllium release. We'll be easily 50+ going with Boron in September. And indeed, you can see the APIs will be different as well, whether you go REST or whether you go native. There's even the JavaScript one, which kind of led me to fear that at some stage over the weekend, somebody will code a one in COBOL. But I think the point is that we'll probably see that software-defined networks is down at the bottom of the trough, which I think probably makes sense. You know, SDN controllers are starting to mature. They're becoming a little bit more robust. They're becoming genuinely data center grade. You know, high availability clustering, many tens of thousands of switches supported, especially by OpenDaylight. And then SDN applications are up here at the top. So our anticipation is we're going to see quite an explosion of SDN applications appear over the next 12 to 18 months. And so we're kind of looking at preparation for that as part of the research. So again, I'm flagging that if you do go and pick a particular controller, it's not easy to port to a different controller without having to rewrite. It's not easy to combine. So if you build up a repertoire or a collection of applications that run on your network, how can you combine them into a super